Alright, so today we're going to start our new unit on exponential functions, and this picture right here is basically just a picture of different types of exponential functions that you could see, and so we're going to look at some different types today. The first thing you need to know is what an exponential function is, what the definition is. So an exponential function is just going to be a function of this form, y equals ab to the x. And so the main thing that you need to notice about this form is that the x is in the exponent, and that's what makes this exponential, okay? Some other important things that you need to remember about exponential functions is, firstly, if your base is 1, b right here is the base. So if your base is 1, the function is a constant function and not exponential. So let's look at why that would be. If we picked a function where the base was 1, let's just pick an easy function like 1 to the x. So we can hopefully see why that base would not be 1. And I choose some x, y values. And I'm going to scoot this up here to make sure you guys can see it, since that video is going to be in the way. So I'm going to choose some x and y values to show you why, if we have 1 as our base, our function won't be exponential, it'll actually be constant. So 3, 4. So hopefully you'll be able to see it after plugging in these 4 values. So I'm going to plug 1 in for x. 1 to the first power is just going to be 1. If I plug in 2 for x, that would be 1 squared, and 1 times 1 is just 1. If I plug in 3, that will be 1 cubed, and 1 times 1 times 1 is still 1. 1 to the fourth is going to be 1, so you can tell that all of those y values would be 1, and that would be the same thing would happen if I took negative values and plugged it in, or continued in the positive direction. So that would give us a graph of a function like that, which is obviously not exponential, because our exponential models look like this. So base cannot be 1 in an exponential model because we get a constant function if it is. Second thing is what I've already said, the variable is always going to be in the exponent. That's what sets it apart and makes it exponential. And then the third thing you need to know about an exponential function is that it has an asymptote. And I want you to understand why it has an asymptote. So let's look at this next slide. So why do exponential functions have an asymptote? The function that I've graphed here and the table that this goes along with is the function y equals 2 to the x. It's just a real simple exponential function. And so you can kind of tell that it has an asymptote right here at y equals 0. And so I want you to understand why, because all of the other functions that we've looked at have been, or had asymptotes when they had somewhere undefined, okay? So this is not the case with an exponential function. There's nowhere it's undefined, but because of the way that this is made, or an exponential function is, you have an asymptote. So let's look at what happens when we plug in positive values for x. Let's see what the y's are. So I'm just going to plug in a few positive values. We'll go up to 4 again. And so if I plug in positive values for x, this would be 2 to the first, and 2 to the first just gives me 2. The second one, if I plug in 2 squared, that would be 4. 2 to the third would be 8, and 2 to the fourth would be 16. So the positive values, you can see that these y's are just going to continue to increase or get bigger, and so that's why on this side our graph looks like it's going to shoot up and continue to shoot up. But now on this side it looks like the graph is just going to get close to that horizontal asymptote. So let's see why. If we plug in negative values for x instead, so I'm going to start with -1, -2, -3, -4, and I think you'll be able to see it after 4. Let's plug those in and see what happens. So if I plug in -1, this would be 2 to the -1. And so if you remember your exponent rules, whenever I have a negative exponent, to get rid of it, I just take the number and drop it to the bottom of a fraction, so that would be 2 to the first. And 1 over 2 to the first in the bottom is just going to be 1/2. If I were to do the same thing with 2 to the -2, 2 to the -2, if I drop that, I would have 1 over 2 squared, which would just be 1 over 4. If I drop the 2 to the -3, let's just plug it in down here. 2 to the -3 would just be 1 over 8. 2 to the -4 would just be 1 over 16. So all we're doing is just taking these numbers that we got here and sticking them in the bottom of a fraction with 1 on top. And so hopefully you can see that these fractions are just going to continue to get smaller. And these fractions over here match these decimals that go along with this table. And so these decimals and fractions are just going to keep getting smaller and smaller and smaller. They're never going to actually be 0. So that's why we have this asymptote right here. This line approaches 0 but never actually touches it because that fraction just keeps getting smaller and smaller. So that's why we have an asymptote in an exponential function. It's always a horizontal. Alright, so there are two types of exponential functions. The first is a standard exponential. And this is just where you have a number, any number, for the base. Okay, any number except 1. So the next is a natural exponential. And hopefully you've seen this before. We'll talk more about e in a second and where it comes from. But this is just when you have base e, okay, as your base. So e is your base. Now, I have a paper folding activity. We're going to skip that slide for now. But I have a paper folding activity that I want you to do. So I'm going to explain the paper folding activity. And after I do, I want you to pause the video and then do the paper folding activity, and you can pick up to see the examples of how to do the worksheet that I'm going to give you after that. So with the paper folding activity, what you're going to do is the paper folding activity is going to be located on the same haiku page, but in a Google Doc right below it, embedded right on the page. So if you pause this and look down there, that Google Doc should be there. But for the paper folding activity, there's two parts. The first part, you're going to start with a piece of paper that has not been folded. Okay, so it's just a piece of paper like this. And so if you'll notice on that paper, it says for part 1, step 1, you want to fold your paper in half and determine the number of sections the paper has after you've made a fold. Okay, and then for number 2, it gives you a chart. And over here, this is the number of folds. This is the number of sections. So I'm going to start out with folding my paper 0 times. Okay, so I'm just going to gather some data by folding this paper. So if I do not fold this paper at all, this is 0 folds, then I have this one big section that my paper makes. Now, if I fold it once, okay, so if I fold my paper one time and then open it back up, I can see that there are 1, 2 sections of my paper. Okay, so what I want you to do is finish by folding as many times as you can and filling in the table on the paper folding activity handout. And so then it's got questions 3, 4, and 5 that we'll go over later. And I'll make a separate video for you can go back and look at. But I want you to try this one on your own right now, and then you can go watch that video to see the whole paper folding activity. Alright, the second part of the paper folding activity, it's going to ask you to find the area of the smallest section. So, the area problem, this is part 1. That's how we do part 1. And I'm going to take this and move some stuff around so we can make sure we see it all. So I'm going to move this over here. Now, part 2 asks you to find the area of the smallest section. So you're going to put number of folds here. And this is all in a chart on the paper that I'm going to give you. Or that's on the haiku page. And this is the area of smallest section. And I'm just going to abbreviate. Alright, so number of folds. If I fold this paper 0 times, the area of this paper would be represented by the length times the width. So you're going to need a ruler for this. So you would measure the area, okay, or the length of this paper, and then multiply it by the width of this paper. And so then you would find your area of the smallest section. And so this paper I know is 8.5 by 11. So 8.5 by 11, oh that's the wrong thing. 8.5 by 11, I would just multiply that in my calculator, and when you do that, you should get 93.5 inches squared. So I want you to do this in inches. But that's how you would do that. Now, once I fold it one time, you would have this one side that's still 8.5, but then this other side, this is the smallest section, but then this other side, that's a different length. So you would need to measure the length and the width, multiply that, and put your area here. And then you'll have questions 3, 4, and 5 to answer on that as well. So you'll finish this, so pause it right now, and then you'll finish this activity on your own, and I'll post another video to show you how to do that activity. So that's how you're going to start out, and you'll finish that on your own. Now, once you finish that, you can pick up and push play. So we're going to look at some applications of exponential functions. And so the main applications that you'll see with exponential functions deal with money. And so these are compounding interest formulas or applications that we're going to look at. And so there are a couple of different ways that you could compound money. So this is saying, like, if I took some money and I put it into a bank account, that account will usually earn some interest. And so when I compound my money, what I do is I take the interest that my money has earned and I add it to my original amount. And then that new amount starts to add or earn interest, okay? So the more times I compound my money or add my interest to my original amount, the more money I'm going to have. So the more times you compound, the better it is. So this is the formula for a problem that says I'm compounding my money a certain number of times a year. These are the different amounts that you could see. So I could compound my money yearly, which would be once a year. Semi-annually would be twice a year. Quarterly would be 4 times a year. Monthly is 12, weekly is 52, and daily is 365. So you guys know that and are aware of that. But let's talk about what the variables in this formula means. A is just going to be your ending amount, okay, or what you end up with after your money has been compounded a certain number of times a year for a certain amount of time. P is going to be the initial. What does initial mean? It just means initial. I can't spell. This just means the start amount. The rate is going to be, or R is just going to be the rate. You have to make sure you plug this in as a decimal. N is just the number of times you compound your money. So that's where you get your yearly, semi-annually, whatever the case may be, over there in that little thing. And then T is just the time. You have to make sure this is in years. Okay, so let's look at, this is our standard compounding interest formula for compounding it a specific number of times a year. Sometimes you're going to compound your money continuously. And so that's when you use a natural exponential function, and this is an application that uses base e that I talked about. And so e is just another number like pi. So it's just 2.71828, and it just goes on forever. Okay, so it occurs often in exponential applications, and a lot of times people will just say, here's e, you use it in compounding continuously applications. But I want you to understand where it comes from. So let's look at this website that I found that I think does a real good job of explaining where E comes from. So if we just disregard the principal amount, because it's going to work the same for every amount that we would start out with. So the principal would just go in front of this parentheses right here. But I'm going to look at what happens to this base, okay, the base in my problem, because E is a base. I'm just going to look at what happens to this base as I compound more and more and more often. So if I compound yearly, that's once a year, and so I plug in 1 for all of these things, and I just get 2 as my number that my base would be. If I compound semi-annually, that is going to make that base a little bit bigger, okay? And that would be 2 for my number that I plug in for N. For quarterly, that would be 4 times a year, so I would plug in 4, and then the number goes to this. Monthly, weekly, daily, hourly, every minute, and every second. So all of these numbers are getting closer to continuous compounding. And you can look and see what your number, or what your base, is getting close to. And guess what? It's the 2.718282, blah, 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 and it goes on. And so I just think that's real neat how that happens like that. And so that's where that E comes from. It's not just a random number that's just pulled out of the middle of nowhere. And so E actually represents something. So that's what you're going to use whenever you compound continuously. And so for compounding continuously, we're going to use PERT. So A is your end amount. P is your start amount, or your initial. E is the base. That's just the 2.718 number. You're not going to plug anything into that. R is the rate. You plug again as a decimal. And then T is your time in years. And I'm about to run out of time, so we'll stop here and go on to part 2, and I'll show you how to do these application problems.